Hello everyone, thank you all for coming. My name is Augusto. I am a software engineer at Datadog. I work at a performance engineering team, and my work mostly focuses around benchmarking tooling.
Yeah, hello, my name is Kemal, and I also work for Datadog. I am part of language platform team, which maintains client libraries for instrumentation with all the languages. I am accidentally here because I was seeing all these PR comments on our PR says that, oh, there's a performance regression, whatnot. And I dive deep and saw that it's something cool. And I asked Augusto, why aren't we giving a talk about this now that there's this software engineering dev room? And he said, why don't you do it? So now that's how we are here. So let's start with the basics. So performance matters, period. So it matters because low latency systems, we will see some numbers on these, but it creates, if you have more performance system, if you pull down your latencies, it will affect the user experience. And then you will have high throughput on your online systems, or the queuing systems. And in the end, it's the better user experience. This could be whether a UI UX app, or it could be any CI app, or anything. You would feel these latencies. And on that, we gathered a couple of studies. You can see that on our references. So according to at some certain point of time, Google measured that 20%, the 500 millisecond delay caused 20% of traffic drop. Same thing happened with the Yahoo. If you just make things 400 milliseconds faster, you got 5 to 9% more traffic. And these numbers are old. Probably these are more sensitive right now. And when it comes to the cloud cost, because of all these performance things happening, this is $675 billion. It's hard to imagine. Apparently, there's a market for that. So if you're in this business, go for it. So yeah, tech talk without a quote wouldn't count. So this is my first quote. This is from Toby Lübke, from the CEO of Shopify. This is one thing that we need to understand, right? It's maybe not the first-class feature of our software system, but performance is always counts, and the all world-class software is they are fast. So when it comes how the user perceives these differences and how they are noticeable, if it's order of hundreds of milliseconds, it's just minimally noticeable. But if you go up, then you can see that users are actually switching away. I'm sure you feel this, right? If you're developers, even I feel that every day because of the CI runs. I hate CI, and this is my pain, right? It says 5 to 10 seconds. We have some CI systems 30 minutes. It's killing me. So if you want to get just one thing from this talk, this is that. Write benchmarks, but run them continuously. Probably we're going to talk about that, but probably the benchmarks you have also wrong. So we will also talk about that, how to make them right. So a quick poll, who has written a benchmark here? All right. Yeah, this is software performance. I should have seen this coming. So who has been surprised by the result? All right. Okay, we have our audience. So, but first, why software is slow? Why these things are happening? First of all, CPUs don't recognize the bad algorithms. If you have put something wrong in there, CPUs won't make it faster. Same goes for the compilers. You cannot rely on your compilers if you are using a compiler, by the way. I hope you're not writing Python, Ruby. No? Okay. So compilers won't solve all your problems, right? And then we always have this notion of we have asymptotic notation, so we write our algorithms, we measure, or it's ON, whatnot, but then you don't think about the cache misses, branch mispredictions. So this is called mechanical sympathy. So you need to understand underlying system and optimize your workloads for that. So according to another recent study, by giving attention to these details, they actually sped up like 60K times faster by just like tuning these things, right? This number is enormous. You can check the reference. It's cool. So how to design benchmarks? I think there's two major things that you need to focus on. First, like how your representative of your workload is, and then is your results are repeatable. And repeatability requires a lot of science that I'm having a hard time to understand. I will hand it over to Augusto when the time comes. So before we segue to that, we need to classify what are the benchmarks, and for that, I call this part is the art of writing benchmarks, because you need to decide whether you would like to have a micro benchmark that you want to write or a macro one. So when we say the micro benchmark, it is like isolated functions, operations, like nanosecond precision, the thing that you put on your unit test. If you are using Go, you have an advantage. There's first class facilities to do that, but they are not representative. They are micro benchmarks. I should have put a Knut quote here, like the premature optimization is the root of all evil. It was mandatory, but I forgot about it. So that falls to the same category. Okay. Oh, you really missed all the things that I said? Sorry about that. Okay. And then the macro benchmarks is about your end-to-end test flows, realistic workloads. They have higher variance because you are doing a lot of stuff. Maybe you are talking to other systems, whatnot, but they are actually closer to what you are doing in the production. And it's hard to isolate the causes. You can maybe run a continuous profiler or take a profiling snapshot while you are doing this and try to optimize, but still these are the benchmarks. What you can additionally do is use a production observability system, platform, shameless flag, and then you can discover your production things, what's going on, and you basically know more about these things. So choose the right tool for the right job, but in the end, it's a mashup. Basically use both of these strategies and use your judgment and find the bottlenecks and optimize. So when we talk about representative workloads, what are they? They could be, your applications could be CPU ones, maybe I/O ones, maybe you are in a mixed position, maybe you are saturating your memory bandwidth. You need to understand and try to find the correct representative workload for your benchmarks, right? For that, what we try to come up with is some sort of archetypes, right? While we are designing our macro benchmark tools. It could be an idle app mostly sitting there doing nothing. It could be low latency or latency sensitive application, or maybe it's a throughput sensitive application, or it's a mixed bag, right? We call it enterprise. You have a bit of everything. And then we run all these things and try to get all the numbers and try to react to that. We are obsessed with this because all the libraries that we write, we put them in the production services of our users, and then if something happens, they actually blame us. I included that, and okay, this break my system because we just make this observable. So we are trying to be super sensitive about it and reduce all our workloads for that. So how to design benchmarks? This is where the science starts. So I'm leaving that to Augusto.
Okay. So we have seen that benchmarks have to be repeatable and representative. We are going to focus on the repeatable part now. And the idea is to take a benchmark that wasn't repeatable in the beginning and try to make it better with some few changes that we're going to do. And often in my job, people come to me saying that, oh, I got this benchmark and it's not repeatable. What can I do? And this is usually my first reaction to this. And the benchmark itself has the goal of measuring dtrace Java, which is one of our libraries, instrumentation overhead on a Spring app. And it's a really simple app just made for this benchmark. The system under test was the app instrumented or not with dtrace Java, so we could measure the overhead. The workload was as many requests as possible by 5 concurrent users. We wanted to measure the system at a really high load. And we separated it into 2 stages, a 20-second warm-up and 15 seconds of actual measurements, okay? Cool. We have these initial results, and they look right? We have the warm-up, and it seems like we have cut the data points at a place that makes sense. But actually, no. We had many false positives, so the benchmarks were telling us that we had some improvement, when in fact there wasn't really an improvement. And we had a really high coefficient of variation, and this is just a way to measure the variation of a sample, and it's the standard deviation divided by the mean. And it was 11.80%, which was unacceptable for this use case. So the first question that I asked myself was, okay, are we running the benchmark long enough? Is this really the warm-up? Turns out that no. It actually took way over 20 seconds. It took a little bit above 150 seconds to warm up. And so tip number one is to run your benchmarks for long enough so that you can uncover perturbations. And one of such perturbations have to do with warm-up, okay? Cool. Ideally, we could be able to run benchmarks for a really long time and get consistent results, but we don't have infinite money to do that. So we have to choose when to stop. And for how long should we run the benchmarks? To know that, you have to experiment. And here's an example of experiments that we do. We take the measurements and cut them at different steps to understand how the variation behaves. So for example, at 30 measurements, we have a 7% coefficient of variation. And when we go to 90, we have a way lower coefficient of variation of 4.6%, okay? But it will all depend on the benchmark that you want to do and what you want to measure. Tip number two is therefore to collect enough samples to reduce intra-run variation. And a good rule of thumb is to have at least 30 samples for that. Okay, but if you run this benchmark several times, you might even still get different results. There is something we call inter-run variation when you run your benchmark multiple times and you see different results like this. This is a screenshot from a paper that we referenced internally. And it's measuring the initial state, the impact of the initial state on FFT benchmarks. And you can see that on every run, separated by the vertical lines, we have a different latency measurement. We can do the same for our experiment. I ran it 5 times. And by plotting the graph in a similar way, we see that the same effect happens. On every run, we have different measurements. So we have to take that into account. When we see the results, and you don't really need to read all of this table, just focus on the mean values, which concentrate around the same value of 20 milliseconds. So we know the benchmark is consistent. And if we aggregate everything, so in the last row, we see that the coefficient of variation is way lower at 3%, which is already a good spot. Tip number 3 is therefore to rerun benchmarks so that you reduce this inter-run variation. A good rule of thumb is to run it 5 times. But again, this is something that we use internally. It depends on your problem. By applying these 3 tips, we got the coefficient of variation down from 12% to 3%, which is already great. But there are more tips that I would like to briefly talk about. I don't know if we will have enough time. The first one is to use deterministic inputs. If you have random inputs, you will have random outputs. So that is not good for repeatable benchmarks. And the next one is to use load generators that avoid coordinated omission. And coordinated omission is when your load generator synchronizes with the system under test in a way that you get artificial latency results. So if you have a slow system, the load generator slows down, and then you have artificially better latencies. And if you want to measure your system at a high load, as it is in our case, this won't cut it. There is a really good talk by Gilles Tenney about how not to measure latency, where he goes really deep into the subject, so I highly recommend it. All right, so you have a well-designed benchmark. You are getting results, but you cannot rely on simple aggregated data points to tell the whole story. You've got to look at the entire data, and the aggregate values won't tell you that. To show you an example, suppose you're working on a project and you make several commits, and at some point you decide to make an improvement. So you make an improvement and you see some improvement on the throughput, okay? But is it really an improvement? By looking at the mean throughput, you can't really know. Zooming in on these 2 last commits and their benchmarking results, we can see that there was maybe an improvement. But if we plot all of the data points on a histogram like this, there is quite a lot of overlap. So maybe if we have ran this experiment another time, we wouldn't have the same conclusion. And we have to somehow evaluate how big the difference between the first and the second one is to make an adequate conclusion. So the question is, how can we tell if the difference is big enough? First of all, we see that there is some spread in the data, right? So we have to compare the difference with the noise. So we can set up, wait up, I forgot about this, but yeah, I won't get too much into the math. We can just focus on the intuition for now, because otherwise we would be here for a long time. So we can set up a simple ratio like this to tell if the difference is big enough. All right, so we compare the difference with the noise. We can call this guy T, okay, just to simplify things. And if T is bigger than some critical value, then we can say that, yeah, there was an improvement. Okay, how to define this critical value, right? Mathematicians have thought about this, and it turns out that you can plug in a false positive rate, which we call alpha, into a formula, and you get a critical value. And this false positive rate is something that you can control to, as a trade-off, to detect more things or to detect less things, but you are also going to detect more false positives or less. It depends on what you want to do. So for example, if we have a high false positive rate, we are going to detect more things, but also more false positives. Cool. And we can write the critical value as a function of alpha. And mathematicians, as I said, they worked really hard on this. There are formulas that you can look up, and the critical value is notated like this. And in fact, this is a hypothesis test, okay? And it's a t-test specifically, and this is why the name of that ratio is t. But that's all for this talk. I won't get too much deeper into it. There are other approaches for that. One example is change point detection. And for that, you can check out Henrik Engel's talk at 1:50 p.m. on this room. So be sure to check that out. Tip number 6 is therefore to use statistics, for example, hypothesis testing, to see if your performance improvements or regressions were statistically significant. Cool, but what if you run your experiment in the morning and then in the afternoon? Especially if you're using cloud environments, you're likely going to get different results, okay? The mitigation for that is to control your benchmarking environment, okay? And this is, in fact, so important that it's actually tip number 0. Otherwise, all of the other ones are not going to work. And we are going to try to see how we can do that, okay? All right.
Are you still with us? Number part is kind of over.
Yeah.
So you can be relaxed.
Now we have a story. So imagine you are a researcher and you're trying to measure the speed of a subatomic particle called the neutrino. And the neutrino is a really small thing. You can't really measure it on your laptop on a desk. So you got to build a huge tunnel for it. And we had people here giving the previous talk, Max, which was an amazing talk that talked about CERN. So you build a tunnel from CERN to Gran Sasso, a 730-kilometer tunnel, so you can measure the speed of the neutrino. And it takes a long time and a lot of money, but when you start getting results and people are publishing papers, everyone is happy. But at a certain point, you start breaking the laws of physics, right? And this shouldn't really happen. So you double check everything, you check the math, the sensors, you check and double check everything until you come across the root cause, which isn't a revolution in physics, but it's a loose cable. So this goes to show that really small things can impact highly controlled environments in a big way. Okay? Most of us aren't building 730-kilometer tunnels. Some of us are. But we have to deal with this, so to speak, loose cables every day when we are working with software performance. This is a non-extensive list of sources of noise and mitigations that we can do. We are not going to talk about all of them, only these ones, okay? This is already quite a lot, so I have to go a little bit fast. All right, first one, virtualization. The problem with virtualization on cloud environments has to do with the noisy neighbor problem, which means that on a single host, you will have multiple tenants competing for resources. And this will give you non-repeatable benchmarks. The mitigation for that is to use bare metal cloud instances. And besides getting rid of the noisy neighbor problem, the kernel and CPU layer mitigations that we are going to see on the next slides requires bare metal access. Bare metal access is basically you have access to the hardware of a dedicated machine. Okay? These are the kernel level mitigations. They have to do mainly with scheduling and caching. They are setting CPU affinity, process priority, and warming up or dropping caches. Here we are dropping caches. And I won't get into the commands themselves, but this is something that you can copy and paste and immediately have a more repeatable setup. With regards to the CPU layer, we have simultaneous multi-threading contention and dynamic frequency scaling. They are a little bit trickier, so we are going to see each one separately. So simultaneous multi-threading, SMT, is when you have multiple hardware threads running on the same core. So you are going to have some resource contention if you have CPU-bound processes, okay? To disable SMT is just, you can simply run this command on Unix machines. And the impact of disabling it was measured by a really simple experiment. So we had a bare metal instance, and with dynamic frequency scaling disabled, which is the other CPU layer mitigation. We are using 2 CPU-bound tasks on the same core versus separate cores. And we can see clearly that when we are running things on the same core, there is contention, so the latency is higher. And if we look at the numbers, the coefficient of variation goes down significantly from 24% to 0.24%. So this is 100 times less variation, which is huge for a really simple trick that you can do. Okay? Dynamic frequency scaling is when your CPU works harder for harder tasks and works less hard for easier ones, so that you save energy. But this is terrible for repeatability, right? So it matches the workload, and you don't really want that for repeatable experiments. To disable it, it is a little bit more complicated. You have to pin the clock rate to a frequency that you want. Then you have to control the scaling governor, which is a kernel subsystem, to make it use this clock rate. And then you have to consider things like frequency boosting, which are features of modern CPUs as well. And you have to disable them, okay? The impact of disabling DFS was also measured by an experiment. And here we were measuring the latency on a varying number of CPU-bound tasks on the same core with DFS on versus DFS off. And here, of course, when we have DFS, we have a smaller latency because the CPU works harder. But we can see that the variation is quite bigger when we have DFS, which we don't want. Again, you don't really need to look at all of the table, but you can see that the coefficient of variation drops significantly when we are looking at DFS for one task in comparison with no DFS for one task. In this case, it's 10 times less variation. And of course, there is the caveat that these experiments were made specifically to test this, but it was a way for us to test the boundaries of these mitigations. Okay? Those experiments were run by my manager, in fact, Dmitry Yurchenko, so kudos to him. And this CPU, oops, wrong button. The CPU level tweaks were mostly sourced at Denis Bakalov's book about performance analysis and tuning on modern CPUs, which is a really good reference on this, okay? There is another source of noise which has to do with vibration. And the mitigation for that is to not shout at the data center. And in fact, it actually happens. So this is Brendan Gregg, performance engineering legend, shouting at the data center and seeing some disk I/O latency spikes. So don't shout at the data center.
So after like all these cool stuff built, and they are doing the maths, whatnot, but as a developer, what we see. So first of all, like, let's check out the architecture. This is a really simple one. What we do is like GitLab is an implementation detail, but that's where our like CI builds work. We run these on Kubernetes runners and collect the data, store them in an artifact storage, S3, whatnot, for like later analysis. We have a specific purpose-built UI where we analyze them. We also gather like metrics out of them and push that to our like dashboards. And then the action part comes where like all these statistical analysis tools run on the data that we aggregated, and they send comments to the GitHub, PRs, or they block our releases. So you can think the whole system like the action part is like that is the alerting part on your monitoring system, and the rest of the things are just like collecting data, having dashboards, whatnot. So that feedback loop, how does it work? As we talk at the beginning, we segregate them into two classes, is the micro benchmarks and the macro benchmarks, right? We run micro benchmarks for each PR. These are the benchmarks that are written for the people that actually write these client libraries, and they know like what to measure, and they write these benchmarks for themselves, and it gets run. We do the static analysis, and if something is not looking right, we send these comment messages to the PRs. And these are actually like basically merge gates, so you cannot merge the PR without like addressing these concerns. Right? This could be anything on like maybe you're increasing the memory, maybe you are like introducing higher CPU usage, whatnot. In theory, yes, sometimes you are adding a feature and then you need to say that, okay, like this is somewhat something I was expecting. But most of the times, all right, like what did I mess up? And you go back, run the benchmarks locally, collect some profiles, and try to optimize these things. And the second flow is about running the macro benchmarks. These are the representative loads that I mentioned previously with the archetypes and everything, and then we run them. If this is a virtual machine environment, we even like warm the machines, as like Augusto mentioned. We have different type of like archetypes plus like lower higher put workloads, higher throughput workloads. Like we run a bunch of scenarios, and then depending on that, if we also set SLOs in our benchmarking environment, and if those variations are like not breaching our SLOs, then we allow releasing these libraries. But if they do, and then we go back and focus on how we optimize those things. This is how you see like we get notified by a blocking release. It's just Slack message. Everybody uses Slack nowadays. So, and then we have dashboards on the SLOs that we put, and we also can go and like analyze what is going on depending on the scenarios, and we have like different severity levels, and then we actually, even though we don't breach anything, we also check out the trends and where they go. And we have a thing called Operation Excellence meetings, and we check these dashboards and try to understand what is the trend, why this is happening, and we try to be proactive and fix these issues before they hit the production. So this is what we built. It's not open source, unfortunately, not yet. This is not something we're going to sell, so we plan to make it open source. But right now, these are the tools that they are actually you can use. Like Hyperfine is a CLI benchmarking tool, and it already handles running your benchmark a couple of times and collect data analytics, and it is better than most of the tools. Or if you're working with Go benchmarking facilities already does this for you. I think, like Henrik going to mention about the GitHub Action benchmark in more detail, but it's something that you can immediately use right now if you are running your benchmarks on GitHub Actions. And like, what is the key takeaway in the end with all these things in mind? So control your benchmarking environment. So this is the most important part, I guess. Like try run your benchmarking on your benchmarks on bare metal machine in isolation. disabling SMT and disabling DFS. Unfortunately, you can't do that on a virtual machine environment. So like out of the box, GitHub Action Runners won't help you. So you need a solution for that. And design your benchmarks to be representative and like repeatable. That's the other most important thing that Augusto already mentioned. Like there are a lot of variations going on. And then like interpreting the benchmark result is the most important part in the end. Maybe there could be false positive. It's like there is no way to automate these things, and you just need to use your better judgment, or maybe just rerun your like benchmarks again. So, and then for us, like from a user's perspective, integrating benchmarks into your workflow and continuously optimizing your workloads and be aware of like basically have a performance engineer mindset, it pays dividends in the long run. But maybe the most important part, don't shout to your data centers. Maybe we don't use the HDDs anymore, but now we have AI lords in there, so make sure you don't shout at them. So for that, thanks for
I fully understand wanting to reduce the noise and variance, but if I'm targeting desktop and laptop machines for my software, I feel like, for example, disabling multi-threading is kind of lying to myself because I'm not representing the machine as it is. So what do you do with that?
I couldn't hear entirely the question.
So if I'm targeting desktop and laptop machines, I feel like if I disable multi-threading to reduce the noise, it does reduce the noise, but then I'm not being true to the actual machine that it would run on.
In this case, there is a clear trade-off. There is a clear trade-off between representativeness and repeatability, right? So in our specific case where we need to have repeatability, because we are running benchmarks on every PR and every release, we needed to disable them. And if you need more representativeness, as we do for some tests, we keep them on and we see what happens if we have those things on. So I think the better answer is to run everything. That is probably not possible. So it depends on what you want to really focus on.
One of the tricks that I do, like locally, use Docker Compose and try to isolate the CPU sockets with the Docker containers, and like as much as possible try to make sure that that container is attached to a single CPU set, whatnot, locally that happens. But otherwise, there are, if you're like running it not on even Linux, it's even harder.
Yeah, thank you for the question. This is a really important point.
Sorry, I had one more question. So during your talk, you mentioned that so an important aspect of benchmarking is to test. So we have to test your environment, making sure it tests well, and as you said, we don't know for how long we want to test, and it costs money to test. So the question I had in mind was that, was there any perspective of instead of testing, expecting the result? So for example, using machine learning models or deep learning models to expect the result, which would maybe cost less, it could be accurate. So I wanted to ask if you have any information or opinion about that.
Mm-hmm. My team has already researched a little bit about performance models. We have not gotten too much deep into it because I think it was less costly to simply get the benchmarks running. It would take too much developer time for us to focus on this problem itself. So we had this in mind. We're probably going to look into it because now we are running more and more benchmarks. But for now, it is not something that we have looked into. But that is a really good thing to look into. If it can be done well, you can save a lot of money and really predict at maybe not at a really accurate level, but predict in a general sense the performance of your system. Yeah.
Thank you. Are there any other questions? Okay, then. Thank you for your presentation.
All right. Thank you.